We've been talking about probability theory in chapter 4. Now we're going to talk about probability distributions. And the first type we're going to talk about are discrete probability distributions. So recall, before we get to the recall, let me give you the first new term, which is a random variable. And a random variable is a variable, and we typically denote it by the letter X that has a single numerical value. So the random variable is a variable that has a number associated with it, and it's determined by chance for each outcome of a procedure. So then the probability distribution is each of these random variables, the values of the random variables, with their given probabilities. For example, suppose I was looking for let X be the number of girls out of 3 girls. So the possible values for our the number of girls out of 3 children. So the possible values for the random variable would be either no girls out of 3 children, 1 girl out of 3 children, 2 girls out of 3 children, or 3 girls out of 3 children. So the random variable X, which stood for the number of girls out of 3 children, can take on the possible values of 0, 1, 2, and 3. The probability distribution then would be each of these values with their associated probabilities. Now, I'll show you later how we find these, but the probability of having no girls out of 3 children is 1/8. The probability of having 1 girl out of 3 children is 3/8. The probability of having 2 girls out of 3 children is 3/8. And the probability of having 3 girls out of 3 children is 1/8. So the probability distribution is each possible value of the random variable along with its associated probability. Recall from chapter 1, we talked about types of data, and we said there was 2 types of numeric or quantitative data, discrete and continuous. Now we're going to continue on with that same idea. A discrete random variable will be a random variable that takes on a countable number of values. For my example of the number of girls, you count the number of girls. So it is a discrete random variable. And we also have continuous random variables. If you recall from chapter 1, continuous data was data that could take on any value on the number line, and those were values that we measured. Well, the continuous random variable follows the same path as the continuous data in that it's a random variable that can take on infinitely many values within the number line, and we can think of them as values that we measure. So suppose the random variable X is the depth of Lake Hollingsworth. Now the random variable can take on any value between 0, if there's no water in Lake Hollingsworth, up to, I don't know how deep Lake Hollingsworth gets, but let's say 8 feet. So any value between 0 and 8 feet. And we would measure the depth of Lake Hollingsworth, so it's a continuous random variable, but we count the number of girls out of a family of 3 children, so that would be discrete. Practice this a little bit. Let X be the number of patients a hospital sees in a day. This means that X is, think about it for just a minute, are we counting this or are we measuring this? We're counting this, so it is discrete. Let X be the cholesterol level of a patient. Now we've got to think, are we counting cholesterol level or do we measure cholesterol level? Think about it for a minute. You're right. We measure cholesterol level, thus it's continuous. All right, so the requirements for a probability distribution are similar to the requirements for just a probability, because a probability distribution does include a probability. So that means that the sum of all the probabilities for all the possible outcomes must sum to 1. And each individual probability must be between 0 and 1 inclusive, for the impossible event is 0 still and the certain event is 1. But all probabilities must sum to 1, and they must individually be between 0 and 1 inclusive of 0 and 1. If the probability is 1, the event is certain. If the probability is 0, that means the event is absolutely impossible. We saw this when we were in chapter 4. Recall, sometimes we rounded probabilities to 0, but they were not truly 0. It was 0.000000001, and to 3 decimal places that rounded to 0. But that's not truly 0. It's just the probability is very small. Again, a good example is the probability of winning the lottery. Well, the probability of winning the lottery is very small, but it is not impossible. People win the lottery all the time. This chapter, we're only going to be looking at discrete probability distributions. When we get to the next chapter, we'll be only looking at continuous probability distributions. So the rest of this chapter will only be considering discrete probability distributions where the random variables will be discrete. In other words, they will be values that take on countable values, such as the number of patients in the hospital, the number of students absent, the number of girls in a family of 5, and so forth. Now, the mean of a discrete probability distribution, this is not a Minitab problem, and it is a pretty messy formula. So let's talk about how we do this. The mean, remember mu stands for the mean, is the sum of the value x times its associated probability, and you multiply each individual value times its probability, then sum up the product, and that will be the mean. The variance is this. Now, I like the second piece of this, where you sum up, you multiply x squared times each individual probability. Then you sum that column up and you minus it from the mean squared, and standard deviation is again the square root of the variance. It's easier to look at this example if we look at it with a problem example from your book. Go to page 184 in your book and look at the table. That will be the number of girls out among 2 children and the associated probabilities. So, for example, let me open my book up to page 184. And we see that if we had the number of possible values for our random variable are 0, 1, or 2. We're only looking at among 2 births. So the probability of 0 girls is 0.25. The probability of 1 girl is 0.50, and the probability of having 2 girls is 0.25. Now let's go to page 187 and look at this table. Now notice how they've set up a third column from table 5.1 that is called x times p of x. And what they did was they multiplied 0 times 0.25, 1 times 0.5, and 2 times 0.25. They then add that column up, and that column is the mean. The sum of that column is the mean. Now to find the standard deviation, we square each of the x's. So 0 squared is still 0, 1 squared is 1, and 2 squared is 4. So instead of using the table 5.3, I want you to set up another table. So your fourth column will be called x squared. And in that column goes 0, 1, 4. And then your next column, let's do a fifth column called x squared times p of x. Now we're going to go 0, times 0.25, 1 times 0.5, and 4 times 0.25. Then add that up. When we add up x squared times the probability of x, you should get 1.50. Subtract 1.50. No, I'm sorry. This slide is written wrong. We're going to be subtracting the mean squared from 1.50. So look at the equals. That's correct. 1.5 minus 1 squared, but 1 squared is still just 1, is 0.5. Take the square root of that, and that will be the standard deviation. The expected value is denoted by an uppercase E, and it represents the average value of all the outcomes, but it is the same thing as the mean. So if I ask you on an exam to find the expected value and you have already found the mean, you are just recopying your answer down. So expected value and the mean are the exact same thing. All right, so now that we've seen the generic discrete probability distribution, we're going to next look at two different types of of discrete probability distributions. The first one we're going to look at is known as the binomial probability distribution. And this is the requirements for a binomial probability distribution is first, the procedure has to have a fixed number of trials. So for example, suppose I'm going to look at the number, I'm flipping a coin, or I'm flipping a coin 20 times. All right, so the procedure has a fixed number of trials. I've said ahead of time I'm going to toss a coin 20 times. Next, these trials must be independent. What happens on toss 2 has no effect on what's going to happen on toss 3. Also, remember from chapter 4, trials being independent means the outcome of any individual trial does not affect the probability in any other trials. Now, each trial must be able to be classified as either a success or a failure. Only 2 categories. So in our case, it's heads or tails. I could also, though, do a binomial probability distribution with rolling a die. And even though there are more than 2 sides to the die, if my random variable x stands for the rolling a 2, then my other outcome would be not rolling a 2. So there's still only 2 possible outcomes. Roll a 2 or do not roll a 2. And the probabilities must be constant for each trial. The probability of tossing a head must be the same each time I toss the coin, and the probability of rolling a 2 must be the same each time I roll the die. Got this definition down right. So is this following procedure binomial? If I survey 500 couples and ask them if they have children, so that's a fixed number of people I'm asking, and are there only 2 possible outcomes, can I answer the question with a yes or a no? Think about it for a second. Yes, because either they have children, yes, or they do not have children, no, and I'm talking to a fixed number of couples. Also, if couple 1 has children, it has no effect on whether couple 2 has children, and so forth. Now let's look at the next. I ask a couple the age of their children. Okay, so think about this. Well, this messes up several, but the most important one is that there are more than 2 possible answers. So someone may say the age of their children is 2, 5, 7, 8, 10, so forth, and so there's more than 2 possible outcomes. The question cannot be answered with a yes or a no. And also, I don't have a fixed number of couples that I'm talking to. Binomial distribution is first. S will stand for a success. In other words, S will stand for getting a yes to your question. F denotes a failure. In other words, it stands for getting a no to your question. Probability of S is the probability of a success in one trial. The probability of F is, we're going to denote it by a Q, and it's going to be 1 minus P from the complement rule that we learned in chapter 4, because there's only 2 possible outcomes. So if 25% of the people say yes, then that means 75% of the people said no. N denotes the number of trials. It's the number in our example with the 500 couples. N stood for 500. X denotes the number of successes out of the N trials. And the probability of X denotes the probability of getting X successes in N trials. When we're talking about independent, if we are dealing with very large populations and our sample sizes are less than or no more than 5% of the population, even when we're sampling without replacement, we can still treat those events as being independent. Normally, if you do not replace, the events are not independent. We looked at this in the last chapter. There are 3 different ways that we're going to calculate binomial probabilities. The first 2 we're not going to spend much time with, but we're going to use the formula, which you'll see in a minute, and it's very messy and you're not going to like it anyway. We have a table in the back of the book. The problem with that table is it only has a very few values of the possibilities. Or we're going to use technology, and in our case we're going to look at Minitab, and you're going to have an entire lab full of computing the probabilities using Minitab. If X is either 1 or 2 or 3 or 0, I should have put 0 in there too. The probability of X being 1 or 2 or 3 is n factorial over n minus x factorial times x factorial times p to the x q to the n minus x. I know this looks messy, and remember, we're not going to be doing it by hand at all. I just wanted to show you what the formula was. If you recall that n factorial is the same thing as what we learned at the end of chapter 4, the combination formula. So for example, suppose n is 6, p is 0.09, which means q is 1 minus 0.09, 0.91, and x is 2. So the formula says n factorial, 6 factorial, divided by n minus x, 6 minus 2 is 4, factorial, times 2 factorial, 0.09 squared, times 0.91 to the 4th, and we get 0.0833. You do not, I just wanted to show this to you. You are going to be using Minitab to do these probabilities. And if you look back at the table A1 in the back of your book, suppose n is 11, x is 7, and p is 0.04. So you look along the far left column and look for n being 11. Then the next column over has x's, and you'll see all the values between 0 and 11. Find the row that has x being 7. Then go across the columns till you see 0.40, where that row in that column inner should be the number 0.025. But notice we only have 1 page of that table, and so would answer very few of our questions. Now Minitab. To use Minitab, we're going to go to the very top. You'll see a button called Calc. Press on that, and another menu drops down. Go to Probability Distributions, then another menu will drop down, and go to Binomial. It's in about the center of that menu there. Then when you click OK, and you're going to, or double click on Binomial, and a box will open up. At the top you see probability and cumulative probability and inverse cumulative. We in this class are never going to use inverse cumulative, so we're just going to use probability and cumulative probability. You select probability if you're looking for the probability that x is equal to an individual number, and you're going to select cumulative probability if you're looking to find the probability that x is less than or equal to x or greater than or equal to x. But look at the little star, so let's go to the bottom of the slide. If you're looking for the probability that x is at least some value x, let's say at least 5, it's 1 minus, Minitab only does less than or equal to. But remember, so it's going to be a 1 minus, it's the complement. But we don't want to subtract out the x because we want to include the x, right? Because greater than or equal to x includes x. So we don't want to subtract out the x. We want to subtract out all the numbers less than x. That's x minus 1. So you had to input, the n was 5, the sample size was 5, the probability was 0.25, and then down an input constant, you're going to enter in 2, but now make sure that you change from probability to cumulative probability, and you're going to input 2 because you do not want to subtract out the 3. Greater than or equal to 3 includes the 3. So we want to subtract out all the values 2 or smaller. So when you do that, when you click OK, you're going to get 0.8965. Then with your own calculator, you're going to do 1 minus 0.8965. And the answer is 0.1035. So about 10.35% are greater than or equal to or at least 3. The third one said strictly less than 3. Less than 3 does not include 3 in counting numbers. So the next counting number down is 2. So we found that in part B. Remember, that value was 0.8965. You are going to get lots of practice with this with your mini-tab lab, and you can also look at more examples in your book. Okay, if we were looking at the last example where n was 5 and p was 0.25, then the mean would be 5 times 0.25, or in other words, the mean is 1.25. If we were looking for the variance, it's 5 times 0.25 times 0.75, which is q, which means the variance is 0.9375, and the mean would be square root of 0.9375, and that is 0.9682. Okay? So that's much simpler than doing that table where we had to do all the values individually. The probability distribution that we're going to look at is known as the Poisson distribution. And the Poisson distribution is still counting the number of occurrences. So it's still a counting thing, the number of, but we're looking at the number of something within a specified time or space, a specified interval of time or space. Examples of this might be the number of accidents on a street corner within a 24-hour period, or the number of defects in a square meter piece of glass. So it's still discrete because we're still counting the number of something, but it's within a specified interval of time or space. So the random variable x is the number of occurrences in a time, area, or volume, right? Time or space. This is the formula for the probability, which again, Minitab's going to do this probability for us, but I just wanted to show you the formula. Our Poisson distribution, or first, x is the number of occurrences over some interval of time or space. The occurrences must be random. The occurrences have to be independent of each other. So if I'm counting accidents, it cannot be that the second accident is caused by the first accident. Those would be considered one accident. It would be an accident, that accident is cleared away, and then 3 hours later another accident happens. And they're uniformly distributed, which means that it is just as likely to have an accident at 8 o'clock in the morning as it is at 9 o'clock in the morning or 9:30 in the morning, uniformly distributed. Now we're going to use Minitab, not that formula. To find the Poisson probabilities, we're going to go to Calc and Probability Distributions. That menu drops down where we found binomial. Okay, someplace in the center near binomial is the word Poisson. Click on Poisson, and you're going to have the same type of box that opened up whenever you did binomial. You have your choice of probability, which we're going to select if we're looking for the probability that x is equal to some individual number. or the probability that x is less than or equal to, which is cumulative probability, and we're never going to do inverse cum in this class. You're going to enter in the mean and the input constant to be x, and then click OK, and Minitab will tell you what that probability is. Suppose I have radioactive atoms, and I started off with 1,000,000 radioactive atoms, and over a year, at the end of the year, I count how many atoms are left. So that's 977,287. So how many atoms have decayed? Well, it'd be 1,000,000 minus how many are left. And if I want the average daily decay, then I need, since there's 365 days in a year, I divide the number that have decayed, divided by 365, and I get 62.23. It is important that we remember that number for the rest of this example. Now, suppose I want to find the probability that on any given day I have exactly 50 atoms decay. So I go to Calc, Probability Distributions, Poisson. I'm looking for the probability that x equals 50, so I make sure I select probability, not cumulative probability. I enter in the mean, which recall from just a minute ago is 62.23. My input constant is 50, and then the probability that x equals 50 is 0.0155. Chapter 5. So now either listen to the lecture again, read chapter 5 out of your textbook, which is on you remember you have an e-version of the textbook in the My Math Lab website. Then go through and do your assignments, your homework assignments for chapter 5. Then watch the recorded lecture for Minitab Lab 5. Download Lab 5, complete the lab by either typing in your answers and saving it as a Word document, or handwriting your answers in and then scan it and save it as a PDF document. And then upload your lab to the portal. Please let me know if you have any questions about the material or the homework or the Minitab Lab.